Everyone. So I know it's been a while since I've made a video, but this video is going to go over the final reactions for the semester for chapter 10, 11, and 12. These are the things you're going to see on the final. It'll be in the synthesis. A lot of them are very important to know, as you'll see as we get into the notes. But so a lot of this is based around alcohol chemistry, and that's like removing alcohols. So with that, if we want to remove an alcohol, first off, we know that OH groups or alcohol groups in general are really bad leaving groups. So it's really hard to get those groups to come off on their own. So what we have to do is basically turn those groups into a water. Waters like to pop off relatively easily, sometimes even spontaneously. They'll come off of the molecule. So, so for removing alcohols, we have two different ways we can do that. We can do substitution like reactions, or we can do elimination reactions. So the first ones we're going to look at are those substitution-based reactions. So this first one we have here is PX3 and pyridine right there. The X right there can be any halogen. So X can be Cl, Er, whatever, whatever halogen you want. And just make sure you're using, so if you use PBr3, make sure that your leaving group is PBr3 or a Br on the molecule. So when we look at our product right here, we get an inversion of stereochem because it's that substitution reaction. It looks something like that if we use PBr. So the next one is substitution using just our halogens like that with like HCl, HBr. Um, once again, X being any halogen. So we can use HBr again. But this time, since we know when we did these types of reactions in test two, that HBr and HCl generate carbocations. So there's really not going to be a specific product. It can be either or. So we can have this, or it can look like this. You can kind of get that racemic mixture we mentioned before for some of the other reactions. And just kind of like to emphasize there's no selectivity because of carbocations. So now moving on to one of the newer things, we have this TSCl impurity. So basically, this reaction is very important for retaining stereochem. So like up above, um, PX3 or PCl3, PBr3, there is an inversion of stereochem, but with this, we get a retention of stereochem. So you can just add the group like this, and almost always there will be a reaction following it. So either an elimination or a substitution. Um, so you won't have to worry about like writing this kind of intermediate step most of the time, but just knowing that it keeps the stereochem, makes a good leaving group, and then we can do substitutions or eliminations. So in this case, we look at our small strong base. So that's going to give us the E2Z product. And then we look at our large strong base, and that gives us the E2H product. And that just goes back to our table, making sure that you know all of the different types of reactions that occur with different types of alkanes and stuff like that. And also in general, for alcohol chemistry, it's very important to know how to add alcohols um, and things like that. So remembering those test two reactions, super helpful. I'm not going to go over those in this video, but if you want to look back, there's a video on those reactions as well. So just remembering that this TSCl retains stereochem. And we'll look at more examples later when I go over the problem set. Now moving on to our elimination. So we have two different elimination reactions for alcohols, but they both basically do the same thing. They're both just eliminating, both eliminate in a Zaitsev fashion. There's one key difference. So EOCl3, we're going to look for that Zaitsev elimination, which is going to be right there. So it's E2Z like elimination. Um, and then looking at H2SO4, it's going to eliminate in the same direction, that more substituted elimination, but H2SO4 is E1 like. And if you remember, E1 is always Zaitsev, but the big thing here is that we can have that rearrangement. So if we had a more substitute carbon nearby, the carbocation could cause that shift, and we could get a slightly different product. But in this case, since there are no differences on the molecule itself, it's going to stay the same. So now moving on, we're going to look at the organometallics. So these are a little bit more complicated. Dr. Berg won't go super heavily into these if he hasn't already gone over them a little bit. But basically, we have three different kinds. We have the Grignard reagent, the organocuprates, and then Suzuki coupling. They're all relatively basic um, once you understand them. They just kind of add a certain part of it, and just being able to memorize that is the important part. So, but with Grignard, this is a little bit more important, especially for semester two. So we break a carbon-oxygen double bond, and we're going to add carbons. That's really the main thing for a lot of these organic metallic reactions is that we are adding carbons to molecules. And then additionally for Grignard, we're also going to get a formation of an alcohol with that. So with Grignard, basically, when we're trying to make it, we're trying to generate a carbon anion, which is a very, very strong base. So when looking at the formation of the Grignard reagent, so we're going to have something with the Br, that's part of it. And then we're going to have the magnesium right there and then dry ether. So when you have all of these things together, that kind of signals that there is going to be Grignard formation. So a lot of times it'll be written out kind of like this. So we'll have one, then Mg, dry ether, and then two is some carbon chain or something. So it really kind of just depends on what the question is asking or what Dr. Berg is trying to get out of the question. So kind of looking at the formation of the Grignard reagent. So this is what it looks like fully together. And this is what it actually looks like. But that kind of, for me, at least is a little bit confusing, trying to see like, okay, where am I adding anything? I don't have any like ions or anything like that. Where's that carbon anion that we were talking about trying to form? But a different way you can kind of look at it is like this. So now we have the separations of charges, and we can clearly see that the anion has been created. So it does look like the one that is highlighted, but for ease of understanding and trying to actually do the reaction, you can kind of think about it with the anion over there. So we can do a quick example. So in this case, it's going to be acid catalyzed. So basically just anything that gives a proton pretty much. So we have our group down here, our anion right here. And this anion is going to attack right there, opening up that bond, attaching there, and opening up that. And then along the way, basically, this little H plus catalyst is going to give that proton or the hydrogen right there to that oxygen, leading to the creation of an alcohol. So in addition to the carbons that added, and they add just like that, right to where the anion attacks, we also have an alcohol thanks to the acid catalyst and with that oxygen being there. You probably won't see this very much on the test, but it is helpful potentially for synthesis, or you might see one or two on the reaction page. Now moving on to organocuprates. Organocuprates are honestly very simple. So if you see like step one has like lithium, step two has copper or something, and then step three has a carbon chain, that's pretty much going to show you that you're doing organocuprates. So basically, whatever is in parentheses, so places BR or your leaving group. So when we look at that, our product is going to look something like this, just like that. Just replaces it. And that's really all there is to it for the organocuprates. Kind of knowing like what it does, what's actually adding is pretty much all you need to know for these. And moving down to Suzuki coupling also works very similar to how the organocuprates is. This whole kind of chunk right here looks big, looks kind of scary. It's not super important. None of that is getting added to the molecule. The only part that's getting added is what's attached to the bromine. So that chain right there, it could be anything. It could be a ring, it could be a long chain, it could be one carbon, but it's whatever is attached to that boron atom is what's being replaced or what's replacing the leaving group. So we look at the product, another simple one right here, just like that. So one thing with both of these, the organocuprates and Suzuki coupling is they can react on sp2 hybridized carbons. So a lot of times we have to have that sp3 carbon to take off one of those hydrogens or something. But in this case, it's able to add the carbons here, which is unique and is very helpful in synthesis and other types of reactions. That's pretty much it for the organometallics. Now we can move on to some very important reactions for both synthesis, and you'll definitely see at least one of these on the test as well as the problem set. So this is the bromination of plain alkanes and alkenes. So like I was saying, this is important because we want to add a leaving group to something that doesn't have anything on there, like a double bond or something like that. So especially with an alkane, there's nothing on there. There's no reaction really to eliminate or create a double bond. So this is one of the key reactions to allow us to create other functional groups on an alkane ring or an alkane in general. So with this, we have Br2, and then we have that H and then the V looking symbol or and then comma delta. So basically, this right here is light and that is heat. So as long as you have Br2 and then one of them, that's fine. You can use the light or the heat. You don't have to use both. One will be fine. So when we look at our product, we draw our pieces on. This reaction wants to add Markovnikov. So it's going to add to that most substituted carbon. So if we look over here, that's 3 prime, 2, and then 1. So that 3 is going to be our best spot to add, and every other carbon on there is 2. So that 3 is our best. And so basically now with the addition of that bromine, we can eliminate and start adding other things, which is really helpful for synthesis. So just remembering that this reaction is Markovnikov. So now another addition of kind of bromine to a ring or to alkenes is NBS and our delta or our heat. So NBS, little note here, will add Br to allylic or benzylic carbons. So when we look at our double bond here, this carbon up here is allylic, and then this one is also allylic. So basically just saying it's kind of within a carbon of where the double bond carbons are, those sp2 carbons. But now these two over here, not allylic. So it won't add there. Now it will only add one, so it's only going to add to one of the two spots. It's the same product either way here because there are no other groups, so it's just going to add, basically going to pick one and add to the ring. Keeping our double bond right there, and our bromine just like that. And that's basically all there is to that one. Just remembering that you can add two allylic or benzylic and then understanding what allylic and benzylic carbons are. So now we're going to move on to the oxidation of alcohol. So this is a nice little chart. It's in the notes. Make sure you understand this, memorize this, whatever you have to do to help you understand it. So basically we have 1, 2, and 3 prime alcohols, and then we have mild oxidizers and strong oxidizers. So an example of a mild oxidizer is just PCC, super easy to write, a lot less to write than the Foley bleach reaction. And then strong oxidizers, you have H2CrO4, and Dr. Berg might write it as K2CrO4, maybe even MnCrO4. I could write it right. So just be looking out. So if you see that CrO4, that's a good sign that it's a strong oxidizer. So look for that, and then just basically memorize the chart. 1 prime alcohols, you either get an aldehyde or a carboxylic acid, depending on the type of oxidizer. And then 2 prime alcohols always create ketones. So it helps to remember with that, super easy. If you see a 2 prime alcohol, you see an oxidizer, doesn't matter what kind it is, you got a ketone. And then 3 prime, they just don't react because that carbon doesn't really have the space to receive that double bond because it already has, it would have too many groups. So it just does a reaction, which is nice and easy. So now kind of moving on to the formation of ethers. So we have two different types. We have acid catalyzed and base promoted. So this first one right here is acid catalyzed, and that's it. Like HCl could be it. A lot of times it will just be written as H plus catalyst or something like that. So just kind of understanding what an acid catalyst is helpful here. So we can start off by looking at our substitution. So this is our most substituted. This is our least substituted carbon. Be a 3 prime and 1 or 2 prime over there. And this comes into play because of the type of reaction that we're going to be doing. So this reaction functions in a Markovnikov way. So it's going to add that our OCH3 to the more substituted carbon in this case. So basically what we're going to see happen is the oxygen right there is going to get a hydrogen. This bond's going to go to it, creating that carbocation right there. And that's where that leaving group is going to go into. So when we look at our product, it's going to look a little something like this. And that's the acid catalyzed formation. So it's SN1 like, it's Markovnikov, and just remembering that 3 prime carbocations are more reactive than 2 prime and 1 prime and so on, and things like that. Now moving on to the base promoted, it's basically the opposite. So this reaction, we're going to have our OCH3 group add to the less substituted carbon. So it's the exact same molecule as the acid catalyzed one. So you can look there. So when we have our product, it's basically just going to switch the position of the alcohol on the ether group. The alcohol is going to go there, and then OCH3 is going to go where the alcohol was for the acid catalyzed one. So this one is more SN2-like, and in this case, the 1 prime greater than 2 prime greater than 3 prime, and it kind of acts in an anti-Markovnikov way. So now moving on to diols, this is very important. I'm pretty sure my synthesis last year had I needed to use a diol reaction, or either there was on the reaction page. We'll definitely see one of the two of these. So we have the cis and we have the trans addition of diols. So for the trans addition, we have the NaOH, H2O, HCl. So the big thing here is just remembering what trans looks like when you're looking at stereochem when adding two groups. So we're going to draw that. That's our base, basically. And then it doesn't matter which one is which, as long as you show differences. So this is the trans product. And then looking at our OSO4, our osmium reaction, H2O2, H2O, we have the same base, except this time both are on the same type of line. They could both be on dashes as long as they show the same symbols to show that they're cis. This is going to be the cis product. Definitely really important to remember those reactions for the test. Now moving on to the problem set, everybody's favorite part of the videos. So I'm going to go through some of them. I may not give the answers for all of them, let you work for it a little bit. But starting off, we have EOCl3 and pyridine. We have one of our elimination reactions. So like I said earlier, this is that E2Z-like reaction. In this case, there is only one way, that's E2 Zaitsev. So we do have that selectivity. Just like that. And looking at H2SO4, so this one is more E1-like. So just knowing that just in case we have some shifting of our um, product or our intermediate step with that carbocation, since it is E1-like, we can look there. So we have CH3, CH2, CH, and then we can kind of look around. Okay, substitutions aren't really different, so we're just going to leave it right there. C, CH3, CH3. And that's pretty much it for that one. And back for the first one, it's E2C. So now with HBr, it's doing that substitution reaction with the alcohol group. Like I said earlier, there's a formation of a carbocation. Very important here because shift can happen. So if we're looking at our potential places, so right now it's on a 2 prime carbon, but right beside there we have a 3 prime, and we know that 3 prime carbocation is more reactive, so bromine's probably going to add there. Moving down the list, we have our first oxidation reaction. So this is bleach, basically household bleach, and just kind of recognizing you only really need to be able to write down one of them for using all reactions, but then being able to recognize the other ones, like bleach in this case. So this is a mild oxidizer. So now we can go and look at our alcohol. What kind of alcohol do we have? So we have one carbon connection, another carbon connection. So we have a 2 prime alcohol. And with 2 prime alcohols, we always get ketones. So it's super easy. That double bonded O right there. That's our ketone. Ketones basically are just in between two other carbon groups. Just like that. Now moving down here, we have our base promoted um, ether reaction. not base ether, base promoted ether. And it functions in the anti-Markovnikov way. So it's going to add our group to the less substituted carbon and form the alcohol and the more substituted carbon for this one. So now moving up to the right side, we have um, our organocuprate. So like I said earlier, it just adds what's in the parentheses. So basically, we're going to swap those two things. So our product looks something like this. And with that, just remembering that this can actually do reactions with those sp2 carbons. If we look right there, that double bond is sp2. A lot of things cannot do reactions that way, but this one can. Very helpful, very nice to know. So now moving on, we have Br2 and we have our light. Like I said earlier, you can use light or delta for heat, whichever one you prefer on the exam. And this is going to be Markovnikov addition. So we can look at our places to add. So we have all the end pieces are always a 1. We have a 2 prime, and we have that 3 prime. So we know that Markovnikov means more substituted. So we're going to add to that 3 prime position, just like that. So now moving on to NBS and delta, or heat. So this is a benzene ring, basically, right here. So that means we're looking at benzylic carbons. So it's going to be the one directly attached to that benzene ring. That's our benzylic carbon. And NBS and delta adds a bromine to benzylic or lilac carbons. In this case, that benzylic carbon would be where you add the bromine. Now moving down to these two. So this is where I was talking about. We have that inversion of stereochem. It can be a little bit confusing, but it's very important to remember this. This is very helpful for like reach selectivity and getting certain types of products or certain types of stereochem products. So to start off, we know that that TSCl and pyridine is going to basically just replace that alcohol, little substitution reaction like that. Keep our methyl group up here. And then we'll add our hydrogens in because they're important. So step 2 is going to be a small, strong base, so an E2 reaction. And now when looking at this, the big thing that we need to remember with E2 reactions is anti-aryl planar hydrogens. So a lot of times we look at E2, in this case, like we're looking at an E2 Zaitsev reaction is what we think a 2' small strong base reaction is going to be. But when we look, there's no hydrogens up there that are on the other plane. So we have to go down and grab this hydrogen on the wedge right there. So our product is actually going to look more like the Hoffman product in this case. Making sure to keep your stereochem of that methyl group up here. And then we eliminate in that direction. You don't need to show this middle step with the OT, but it's just helpful in understanding why you eliminate in that direction. So basically PCl3 is going to do a little bit different. So this causes inversion of stereochem. Pretty much all the other ones do cause inversion of stereochem except TSCl. So just remembering that this retains stereochem up here, at least for that first reaction. So with PCl3 impurity, we have our intermediate right here again. But this time, it flips it and we get a Cl on that wedge like that. And now so we have the hydrogen on those dashed lines up there. Once again, looking for the antiperiplanar hydrogen. We found it up there, and our product is going to be more like the E2 Zaitsev. This is the exact same reagents with small strong base. And we're going to get something that looks just like that. And since we have that double bond form um, on a carbon that's attached to that CH3, stereochem is no longer there because it's now an sp2 carbon, and sp2 carbons don't have stereochem. So now we can look at the other version of the problem set. It's got a couple of different reactions that were not on the first one that will be helpful in kind of understanding what's going on. So to start off, SOCl2 basically functions the same way that HCl, um, PCl3 pyridine would work. So it's just going to give us something like this. And then so that OH is going to give us that chlorine group right there. So now moving down, we have another oxidation reaction. And I said if you see CrO4, think strong oxidizer. So make a little note of that. And then we need to label our alcohol. So in this case, we have a 1' alcohol, and then we get to go back to the chart. So a 1' alcohol makes an aldehyde. I lied. It makes a carboxylic acid because it's a strong oxidizer. So with that, it's going to add something that you don't need to know what a carboxylic acid is. Um, you basically just need to know what it looks like and that a 1' strong oxidizer makes carboxylic acid. Now, if we had like PCC or bleach, then we would have the aldehyde, like I said before. But it's not an aldehyde. That was my bad. It is a carboxylic acid, and it would look something like this. With that, we have that carbonyl carbon, and then we have the alcohol also attached to it, just like that. Moving forward, we have our acid catalyzed with that HCl, so acid catalyzed ether. This one is Markovnikov, and we're going to add that OCH3 to the more substituted carbon and the alcohol to the less substituted carbon. And you can go back in through the notes that I did earlier in the video to answer this one. So now moving back down, so we have SOCl2 and pyridine again. It's going to kind of work the same as before, but since we have stereochem, we get that inversion. So these are going to work a little bit differently than on the other problem set version. We were looking at elimination reactions, but in this one, we're looking at weak bases. So we're going to get SN2 reactions. And if we remember, SN2 reactions on a chiral center gives us inversion of stereochem. So when we look at our final product, CH3 is going to stay on that wedge up there, but our CN group is going to add on the wedge. So inversion of stereochem. So in this case, there were two inversions, so it reverted back to the original. stereochem that we started with on that dash line. Um, and then the next one that we're going to look at, our tosyl chloride or TSCl, is going to retain it and then only invert once. So like we said earlier, retain stereochem. So our first thing is going to look like this. CH3, and it's going to be our OT right there. And then same thing, we have a weak base SN2 reaction, and that's going to give us our inversion of stereochem. So it's going to be the opposite of the one above our TSCl reaction. And I'm moving on to some more. So here we have our diol reaction. So our osmium one, remember, this is cis addition of diols. Diols just means two alcohols. So diol alcohols, pretty simple terminology there. And so when we break that double bond and create our diols, we could also put that methyl group um, on either a wedge or a dash. It really just depends. So if you put that on a dash, then your alcohols need to go on the wedges, just like that. That's all there is to it for that reaction. They're pretty simple, very helpful though, because you can kind of eliminate those groups, do things with those alcohols later on with other some of the other reactions that we've learned in the past few chapters. So moving on to the next one, we have another HBr reaction. I didn't really mention this one in the notes, I don't think, but HBr and peroxides can also be written out as ROR, kind of like that. But you'll probably see it written out with the word peroxides. So usually HBr is a Markovnikov addition reaction, but with peroxides, it switches and becomes anti-Markovnikov. If we look at our carbon chain, so here we have a 2' and there we have a 1'. Anti-Mark means away from the more substituted carbon. So we're just adding to the least substituted. So our product is going to look just like this. Pretty simple with that one, but it is a helpful reaction because if you're trying to create a certain type of double bond with elimination, if you're trying to do like a Hoffman product or something like that, this is helpful to kind of like control where things go by using this anti-Mark addition rather than just adding HBr, which might add somewhere that you don't want it necessarily. Now, looking down at the next one, we have NBS and delta. So once again, that delta is our heat. NBS we know is what allows us to add two benzylic or allylic carbons. So when we're looking at our benzylic and allylic carbons, it's the sp3 carbon surrounding the sp2 carbon. So in this case, our allylic carbon, the bromine will add to one of those. Since it's a ring, it'll add to either one. The product will be the same because you can just rotate the ring around in a circle and it looks the same. So moving down to the next one. So this was kind of what I mentioned earlier. If you see that lithium, the copper, it just kind of signals the formation of that organocuprate. So basically what we have here is the setup first, and it's going to look a little something like this. We have our ring, something like that. That's kind of the formation of the reaction itself. And so then that CH3Br, that Br is our leaving group. We're basically going to swap what's in the parentheses with our leaving group. So that ring will gain a methyl group, basically. That's all that's happening. And then the last one is our Suzuki coupling. So the big thing, this is all that stuff that was kind of like on the end that we didn't really need to worry about. But the big thing is the boron atom. So it's whatever carbon structure is attached to it is going to basically swap with the leaving group, in this case, the bromine. So this is going to swap with that. And another way you can tell is Suzuki coupling is at PDL2. You're going to see that with Suzuki coupling every single time, but it's not really a ton to it. It is confusing a little bit at first to look at because it has a lot of different pieces going on, a lot of different kind of reactions, especially for organic cuprates. There's like you see 3 steps. It can be difficult, but once you get it, you won't forget it. It's one of the easier reactions to remember because there's one step. You're switching groups that are already there. You don't have to do any adding really of anything or adding hydrogens anywhere. It's just switching like connections between atoms pretty much. But that's pretty much it for this video. Make sure you are making flashcards for these new reactions. They're very important not only for semester one, but a lot of these reactions are really, really important for semester two, especially test one and semester two. You will be using a lot of these bromination reactions, the organometallic reactions, as well as some of the like tosyl chloride reactions where we have that inversion of stereochem and stuff. But as always, feel free to reach out, email, group me, come to office hours, and good luck studying for the final exam.